discussing, we stopped at the two-body problem. So what did it say? We derived this expression. Please keep your cell phones away and focus on what we are doing here. R double dot plus mu over R cube R is equal to 0. Okay? This is the two-body problem. Now, this is a, see if this makes sense. Okay? Second order, non-linear differential equation in R. Does that make sense? Does that make sense? Second order, why second order? Second derivative, right? Second derivative in R. That's very critical. Okay. Non-linear because you see this makes it a non-linear. It's R cube. So if you plot R versus this equation, you get it.
What do you have right there with the R cube? What do you have right there with the R cube?
Mu. Here R is the, what is R?
Distance between two masses, right?
No, it's the, not distance. What is this R?
It's the relation of what, 1 to 2, something like that.
Right, it's a relative position of smaller mass with respect to the larger. Okay. Right? If you have, so here this is the, we'll refer this to as the central body, and this as the smaller mass is the orbiting body. Got it? So here R would be, give me an example of what would R be in terms of central body and orbiting body.
It's about like Earth and satellite.
Right. So Earth and satellite, or Earth and Moon, Earth and space station, or Sun and Earth. So Earth and Moon would, this would, the central body would be Earth. Moon would be, Moon, satellite, space station would be the orbiting body. So the relative position. Is this position changing? Is this position a function of time?
Yes.
Yes, it is changing, right? Here, what all are changing here? R is changing, this R is changing, mu is what? Constant. It's GM R, which is constant. Okay, it's called the gravitational parameter. Okay, M is mass of the central body. Okay, so here I'm going to write this as. and this is small m, and we should know that m is much greater than small m, and gravitation is the only force. Okay. And the third assumption is m is spherically homogeneous. What do you understand by that?
So generally a sphere that doesn't change shape.
It is a sphere but spherically homogeneous. What does it mean?
Almost the same. Almost the same. So.
Yes.
Would you put, what's the word after smaller mass?
With respect to,
Oh, with respect.
what's the GM?
This is what we derived, right? G is the gravitational force.
Oh, what's that little go bottom? What's that word?
This one?
Yes.
Gravitational parameter. M is mu is the gravitational parameter. Okay. So here M is spherically homogeneous means Earth, for example, is it spherically homogeneous?
Not completely.
It's not a sphere, first of all, right?
Right. Both of them.
Yeah, there is. It's a oblong. Okay. Is it homogeneous? What does homogeneous mean?
It stays the same.
The mass is equally distributed. You got it? Is it homogeneous? Is the mass equally distributed?
Yeah.
Huh?
Yes.
It's not, right? The core is
Dense.
more dense. As you come to the surface, for example, water, 2/3 of the Earth's surface is water. Is water as dense as rock? No, right? So what we assume is the entire sphere is homogeneous. Earth is a sphere and it is homogeneous. You assume that. Okay?
Wait.
But it's not.
You just, I don't know that. You just said it wasn't.
But we assume that. The derivations are made under the assumption that Earth is spherically homogeneous, or the central body is spherically homogeneous. Okay? Otherwise, this will change. You cannot just use mass, you have to use the inertia problem. Okay?
So question. So what if it's like an asteroid that's not like a sphere?
So in that case, you cannot really apply this. So it will not. It is definitely not spherically homogeneous. Earth you can still assume, right? Because much of it is spherically homogeneous, you can say so. But asteroids, it is not. But there are those taking constants. Okay. Now, what is the solution to? If there is a problem, there should be a solution to two-body problem. Try to understand the context here, okay? What you're interested in is this R. You understand? Would you be interested in this R? Do you want to know where is the orbiting body with respect to central body all the time? If you launch a satellite? You want to know, right? Every second, every minute, you want to know where that orbiting body is with respect to the central body. What is the trajectory? You understand? What is the trajectory it takes? Got it? So that you can predict where it is going to be at a certain given time. Okay? So what we are going to do is we are going to derive a solution to the two-body problem. Yes.
In this R double dot plus mu over R, that R double dot is acceleration, right?
It's acceleration, yes. It's the acceleration of.
The orbiting body.
Yes, absolutely. The acceleration of orbiting body with respect to the center. You got it?
Space and I'm talking. What page is it on?
It's look up page 73. Okay. Before we do that, we'll do something here. Okay. We need to define a term.
Some on figure 2.8.
Look up section 2.4, 72. Okay. Page 72. There's something called constants of motion. What is conserved in the universe?
Two.
What is conserved?
Conserve energy.
Energy is conserved. So what we know is linear momentum is conserved. Okay. Angular momentum is conserved. And total mechanical energy is conserved. Conserved means it's constant. How do you define linear momentum? Anybody? Linear momentum?
Mass times velocity?
Hmm?
Use mass times
Constant
velocity.
velocity. We have m r dot. Does that make sense? What would r dot be if this is linear momentum? Okay, I'll just call this L. L. What is this L?
That should just be good.
Guys, put your cell phones down.
So that is the velocity.
It is velocity, but it is also specific linear momentum. Linear momentum per unit mass. Does that make sense? If you take this and divide by mass, you're going to get specific. You understand what is
Why wouldn't it be vice versa?
Huh?
Why wouldn't it be vice versa? Like, wouldn't you get a more accurate velocity considering your mass? Or no?
You have linear momentum. If you want specific linear momentum, you divide by mass. If you divide this by mass, you're going to get specific linear momentum. So linear momentum is nothing but motion. Okay, as one of you said. What is angular momentum? How do you define angular momentum? Anybody? R cross M R dot. Okay, MV, R into MV. That's how you understand about angular momentum, right? What is torque? How do you find torque? Torque. How do you define torque? Hmm?
We was both agreeing that we're looking at from structures, but we can't remember the equation.
You don't know what torque is?
Pressure, like around the moment.
Hmm? How do you apply torque?
The force around the moment.
Force around good torque. Force into displacement, right?
Yeah.
See, if you have to understand this is very basic, very simple. If you apply a force and the line of action of that force is to the center of gravity or center of mass, it results in, if the force applied is line of action is through the center of mass or center of gravity. Come on here, Chris. Come on.
It won't rotate.
I won't hurt you. Come on.
Say come
Come on here, Ken. Okay. Okay. Turn around. This is, let's say this is torus' center of mass. Okay?
Rotation.
This will result in linear motion. You understand? Come on here, okay? You got it? This will result in linear motion, right?
Right.
I'm applying the same force, but it is off of center of gravity. There's a distance here.
Right.
There is torque. You understand? When there is distance, there is torque. You got it?
I got it. I did that like okay.
Thanks. So you see, there is torque. If I apply that, if it is off of the center of gravity, it results in torque. If it goes through the center of gravity, it results in force. You understand? So force causes linear momentum.
Right.
Torque causes angular movement, change in angle. So this R is that component. You understand? That displacement or that offset. You got it? So here we define something called specific angular momentum, which is R cross R dot. Does that make sense? What we have done here is we have simply again divided this by mass. This is specific linear momentum. This is specific angular momentum.
You wouldn't have to divide that R by M2.
Hmm?
You wouldn't need to divide that R by M2.
This whole thing, when you divide it, it will result in this. The M will vanish. Got it? And once we define this AH, total mechanical energy. What do you know about total mechanical energy?
So
What are the components of mechanical energy? Hmm? Yes, potential energy and kinetic energy. What is potential energy a function of?
That's a velocity.
Mass is higher than gravity.
Huh?
Is it not a function of time?
Is potential energy a function of time?
Displacement.
Huh?
Displacement. No, it's not a function of time. Isn't it a function of
It is a function of position.
function of gravity?
Potential gravitation.
It's a function of position.
Because
If you think about a stone, okay? The stone has a mass.
yeah.
There's gravity.
Yes.
Depending on how high you keep the stone, the potential energy is
Mass times height times
that much higher. Does that make sense? It is simply a function of position or the displacement. You understand? The higher it is, the higher potential energy. You got it? What is kinetic energy a function of? Velocity. It's simple, right? How do you define kinetic energy? Half mv square, right?
Yeah.
Does m change? V changes, right? V only when, if you have a mass, if that mass is, the kinetic energy of that will change depending on the velocity. You understand? So when you throw a stone up, what happens to the kinetic energy?
So it changes positive and negative.
It goes from, yes, it changes. So you have to understand, you have a stone here, okay? You throw it high. The kinetic energy, when you throw it, is the highest. The potential energy is the lowest. When it reaches the highest point, the kinetic energy is zero. And then the potential energy is highest. When it comes back to that same spot, it will have the same energy. You get it? That is what it means energy is conserved. All the time it had the same energy. What was balancing? What two elements were balancing each other? Kinetic energy and potential energy. You got it? So the energy was the same throughout that process.
So when it comes back down, gravity wouldn't accelerate more as it comes down?
Gravity is the same. It will accelerate, but the gravity is the same. It will accelerate, so the velocity increases. The acceleration is the same. Okay. So if you see that all throughout that motion, the energy, the total mechanical energy. So if you look at total mechanical energy, it is we'll talk about this. This is the kinetic energy. Okay, this is specific mechanical, total specific mechanical energy. Right? Again, this you see this is divided by mass. Half mv squared. Okay? And this is mu over r. Again, mu is simply a constant. And r is the position. So this is also a constant in constants of motion. Alright?
Is there supposed to be an end for energy? Is there supposed to be an end for energy?
Now this is specific. Here, again, this epsilon is specific total mechanical energy.
So how does it look when it's not specific? What is the equation for when it's not divided by that?
See this, try to understand this. What are we using for non-specific linear momentum, angular momentum energy? What kind of letters are we using? Capital letters. Okay, this is cap, that is cap, that is cap, right? We are using the smaller case equivalent of that for specific. This is epsilon. Instead of using small e, we use epsilon.
Okay, so are those vectors?
Is this a vector?
Is it?
Is energy a vector?
Scalar.
Scale. Awesome. Scale. Energy is a scalar quantity. This is a scalar quantity. These two are vectors. That's a good question.
Great question.
So let's prove. I'm going to prove this first, okay? That energy is conserved. Or let me first take you through the orbit equation or solution to two-body problem. Now pay attention here, this is going to be a little involved. Recall two-body problem statement. You have R double dot plus so you have R double dot is equal to minus mu over R cube R. Okay, I've just taken this and moved this term on the right hand side. What I'm going to do is post cross with vector h. What is h? Small h? Specific angular momentum. Okay. Can I erase this?
Take two to
So what is this? It says post cross with
With h?
specific angular momentum.
Specific angular momentum. So what you're going to get is R double dot crossed with h equal to minus mu over R cube R crossed with h. I've crossed on this equation with h on both sides. Okay?
Why do you negative?
Hmm?
Why do you negative?
It is negative, right?
Yeah, well, I would ask why would you negative?
Look at the equation. It is R double dot plus mu over R cube R. So if you move it on the right hand side, it will be negative. So here, let's look at left hand side. Alright? It's R double dot cross with h, which is equal to d. I can write this as d over dt of R dot cross with h. Okay. here is a simple proof. D over dt of r dot cross with h is what? R double dot cross with h minus r dot cross with h dot. What do we know about h dot? Roshan,
Yes, sir.
what do you know about h dot?
H dot is the derivative of the angular momentum.
Okay, what do we know about that?
That it's now taken with respect to something more than just angular momentum, just the derivative of it.
You get 10 extra credit points if you tell me what you know about h dot. Anybody? Everything is on the board.
H dot is
Specific.
it's conserved.
He's actually on the right path. H dot is
No, I'm saying,
R dot
do it yet.
cross.
why?
Is that the change?
What do you know about H?
Specific angular momentum. Which H?
H is specific angle.
Specific angular momentum, right?
When I say what do you know about H, you cannot tell me what it is.
Okay.
What do you know about H from the board itself? What do you know about it?
You don't know that.
Huh?
You said R equal
No, you know something about it.
R dot.
What do you know about H? It is conserved. You understand? Huh? No. When I say, understand the question. Okay. When I ask you what do you know about something, what do you know about this computer? If I ask you, you cannot say this is computer. You understand?
It's an Apple computer.
It's not about again. What you know about it in sense, you can say it is on. It is stationary.
Sorry. So listen, are you saying that if you derive any of those, since they're constants, they'd be zero?
Exactly. The reason I'm asking is, if you know that it is conserved, you know that it is constant. What is the derivative of a constant?
Zero.
So what is
You
that
understand?
saying?
Huh?
So what is that saying to the angular momentum?
It is conserved, right? It is zero, right? If it is constant, it has to be zero. The derivative has to be zero. This thing is
So does that mean I get like 5?
huh? Now you said h dot is conserved. I wanted you to say h dot is equal to 0. H is conserved. Its derivative is when something is conserved, it means it is a constant. The derivative of a constant is 0. You understand? If I say something like, what is this?
Zero.
0.
Zero. Why are you putting an underline? Why are you putting an underline?
Vector. So if you want to just maintain that both sides are vector. So here both sides are scalar. So here what I prove to you is this is equal to this. You got it?
Wait, what did you do?
This, if I take the derivative, it will be this, right? But this term is 0.
Right.
So this is this. Okay? Now the right hand side is minus mu over r cube, r cross with h. This can be written as one over r cube, or let me just do this. Okay? I'm just going to neglect this or keep this mu aside for a minute. I'm going to bring it back. 1 over r cube. What do you know about, what is the, how do you express h?
It's,
R dot, R crossed with R dot, right?
Yep.
This is, what do you do with this? Exactly. So you see, that is what you need to, it's back. Right? Minus cap, right? CAB. This is minus 1 over r cube. What is this?
Square.
Would you call it backwood?
This is a back minus cap rule. ABC. We did this in class. And you have done an assignment as well. This, you remember your first assignment?
Yeah.
First problem assignment? R dotted with R dot is R square. Right? Or sorry,
I thought it was R squared.
R dot. Okay? Minus R.
Square.
Okay? So this I can write as minus
What do you mean 1 over r? What do you mean 1 is 1 over r times?
right. So what you can do is,
Yeah, 1 over r minus.
so you can write this as minus R dot minus R dot divided by R square. I've taken 1 R from here, I've taken 1 R from here. Okay, and divide and written that as. So this can be written as R dot minus R dot divided by R square. I flip these two. Okay. So this is first R dot minus R dot R. This one. Minus and minus. And this can be written as d over dt of R over R. Do you agree with this? Think about this, okay? D over dt of this over this. How do you solve this? You apply the quotient rule, right? So it is R into R dot minus R dot into R, right? Divided by R. Got it? So now if you combine these two, we'll finish off here. You can write I'm just going to call this A. Now A can be written as d over dt of r dot cross to k is equal to d over dt of, I'm just going to bring back mu, okay? Mu r cross to divided by r. Okay. Now, can I write this? This implies d over dt of, I'll finish off here, minus d over dt of mu r divided by r square is equal to 0. Right? Again, think and tell me what this is. Apply your
Then we can make that R squared.
this one.
Yeah, should that just be R?
No, if that is r square. Oh, you're right. You're right. Very good. See if this makes sense. It doesn't? This makes sense? I've derived this left hand side here, right hand side here. Okay? I'm writing this as equal to this, and I'm just moving this on the left hand side and applying the derivative to the whole thing instead of one item. Okay. What is this? Joshua? If the derivative of something is 0, what is that something? Okay, it's a constant. Right? I name that constant. This is part A of the derivation. Okay? We are deriving orbit equation. We'll do part B next class. These are the things I want you to learn or think. If something is conserved, what do you know about its derivative?
0.
If something's derivative is 0, what do you know about it? It's conserved. Yes. They are already there.